Dear students, today in this lecture uh, we'll study about the applications of derivatives. We have already studied the derivatives of various functions. We have studied the derivative of a polynomial function, the derivatives of rational functions, trigonometric functions, exponential function, logarithmic functions as well. Now in this lecture we learn about the applications of derivatives, that where should this idea will be using. So in this lecture, first of all we'll be concentrating on critical points of a function, and secondly we'll study about the increasing and decreasing functions, and then we'll be able to know the idea of extreme values of a function, and lastly we'll study mean value theorems. So these four are the major topics of this lecture. Maybe there are some subtopics which will be included in this topic, applications of derivatives, but these four are the major topics. Let us start the lecture from the notes. The first one is for y is equal to f of x. If you are given a function of x, its derivative, the derivative of this y, which is denoted by y prime and hence by f prime x. So the derivative of the function represents the slope of tangent line, which is denoted by m. The slope of tangent line is actually the derivative of the function, and that is denoted by m. It is not necessary to denote it by m, but in certain cases this notation is used. Now let me tell you people that what will be the behavior of tangent line, or we may say that the behavior of a function, that whether that function is increasing or decreasing or stationary. So just look at this picture. We see here that that is a line, and the slope of this line is denoted by m. We see that this line makes an angle which is less than 90 degrees. This angle is less than 90 degrees. So when a line makes an angle which is less than 90 degrees, the slope of that line will always be positive, will always be greater than 0. Remember that. When a line makes an angle which is less than 90 degrees, that angle is called acute angle. So when a line makes an angle which is less than 90 degrees, the slope of that line may be a tangent line, maybe any line, so the slope of this line will always be greater than 0. Similarly, we see here that this line may be a tangent line, maybe any line. This line makes an angle which is greater than 90 degrees, obtuse angle. This line makes an angle with x-axis which is greater than 90 degrees, so the slope of this line will always be less than 0. Less than 0 means negative, and greater than 0 means positive. So the slope of this kind of line is always negative, and the slope of this kind of line which makes an angle less than 90 degrees with x-axis will always be greater than 0, will always be positive. Now you see here that this line is parallel to x-axis. So whenever a line is parallel to x-axis, its slope will always be equal to 0. Remember that we are talking about the slope of line. That may be a tangent line. Slope of tangent line is actually the derivative of function. So whenever the derivative of the function is positive, so that line is just like this one. And whenever the derivative of the function is negative, so this line is just like this one. And whenever the derivative of the function is 0, so that line will be parallel to the x-axis. So whenever a line is parallel to the x-axis, we say that the derivative of the function at that point is equal to 0. We see here this line is perpendicular to x-axis. So that line which is perpendicular to the x-axis, its slope is always undefined. Undefined means infinity. So whenever a line is a vertical line is that line which is perpendicular to x-axis. Its slope is always undefined. So remember these hints. Secondly, look at this graph. This graph is the graph of a parabola, a cap shape. That is a parabola which opens downwards from here up to there. This portion, if you draw a tangent line anywhere from here up to there, so this kind of line, the slope of this kind, if you see this line and this line, that is inclined towards the positive x-axis, and this is inclined towards the negative x-axis. So this line is just like that one. So the slope of this line, the slope is actually the derivative of the function we have studied here. So for this portion, wherever you draw a tangent line, here, there, or there, these kinds of lines are looking like just like this line, and for this line the slope is positive. So for those lines, for those tangent lines, the slope will always be positive. So whenever the slope means the derivative is positive, we see here this function is increasing function. It goes above and above and above. So whenever the slope, the derivative of a tangent line is positive, then we say that that function is increasing in that portion. And just look at this only one point here. If we draw a tangent line, this tangent line is parallel to the x-axis, and whenever a line is parallel to the x-axis, its slope will be 0. Slope means derivative of that function will be 0 there where a tangent line is parallel to the x-axis. And just look at this line. We see here that this graph is decreasing. It goes down and down. It goes downwards from here up to there. So this is decreasing. This graph, this function is decreasing. And if you draw any tangent line anywhere on this curve at any point from here up to there, that tangent line will look like that thing. If you draw this tangent line here, are there, so these all tangent lines will look like this line, and the slope of this kind of line is negative, less than 0. So the slope is actually derivative. So the derivative of this kind of tangent line is negative. So whenever the derivative of the function, the slope of tangent line is negative, then we see that the function goes down and down. It means that the function is decreasing function. Anyways, the third this third figure, we see here that this is a whole graph of a function. That is a graph. So we are searching those points. That is a point at which you draw a tangent. So that tangent is parallel to the x-axis. So the derivative of the function will be 0. So that is the point B on x-axis. So the point B on the x-axis, for this value of x, the derivative of the function is 0, because if you draw a tangent line on this point, that will be parallel to the x-axis. Similarly here, if you take this point is from is obtained by putting x equal to c, so f prime c will be 0. This point is obtained by putting x equal to d, so f prime d will be 0, because tangent drawn is parallel to the x-axis, and so on. So if you look at this point, you can draw a tangent in this fashion, you can draw a tangent in this fashion as well, and you can draw a tangent at this function, this style as well. So the tangent is undefined here. You cannot draw a specific tangent on this point. So this kind of point is called a critical point, and the derivative of the function is not defined at this kind of point. So all these points, all these values of x, a, b, c and d, at b, c and d, we see that the derivative of the function is 0, and at x equal to a, we see here that the derivative of the function is undefined. Remember those things. And just look at that that point. We will study this this figure on the coming slide. So just remember these things, that how could we specify a point at which the derivative of the function is 0. Now here in this slide, we will study about the critical point of a function. Critical point of a function. So the definition of critical point, that is an interior point and the domain. Domain values are those values for which a function is defined in real. So the interior point in the domain of a function, domain means values of x. So those values of x for which the derivative of the function is 0, or the derivative of the function is undefined. So those values of x for which the derivative of the function is 0 and the derivative of the function is undefined, infinity, those values of x are called the critical point of the function. Just look at it's called critical point of function. Now where we use this idea, f prime x is equal to infinity. So f prime x equal to infinity is used when f prime x is a rational function. That is, if you find f prime in this style or in this style, or if there is if the power of x is less than 1. So in all those cases, when f prime is in this style or in this style, a rational function in fraction, so we'll use this idea, f prime x is equal to infinity. So whenever you are asked to find the critical points of a function, then you need to find the derivative of the function and put that derivative equal to 0 to get critical point x of the given function. And whenever f prime x is in rational form, this form, you should put f prime x equal to infinity. So whenever there is a variable x in the denominator and this x is absent in numerator, then we will put only f prime x equal to infinity, not f prime x equal to 0. And whenever the variable x is in numerator as well as in denominator, then we'll take f prime x equal to 0 and f prime x equal to infinity. And whenever f prime x is not in this kind of fashion, then we just use f prime x is equal to 0. I am repeating this statement that whenever f prime x is in this fashion, that the variable x is in the denominator, not in numerator, then we'll put f prime x equal to infinity in order to find the critical point of the function. And whenever f prime x is in this fashion, that is numerator and denominator both contain the variable x, then we will use f prime x equal to 0 and f prime x equal to infinity to find the critical point of the given function. And whenever f of x is a polynomial or not in this fashion, then we'll use only this statement, that f prime x equal to 0, in order to find the critical point of a function. Now look at this figure. This figure is repeated here. This figure was in the previous slide. I have enlarged this figure. We see here that critical point is that point at which the value of the function is maximum. This height is maximum here. Now here this height is maximum and this height is minimum here. That height is in this area, that is maximum here. And we see here that this critical point A divides the graph in this fashion. We see here this graph is increasing up to this critical value. So f prime will be greater than 0, and suddenly this graph goes down, so the derivative of the function will be less than 0. So we may say that the critical values of a function divides a function into two parts, increasing and decreasing. Similarly here, f prime b is equal to 0. So we see here that at this value of x, the height of the function is minimum, and this height divides this graph. We see here that this graph goes downwards up to here, and then from this point this graph goes upwards. So this point divide the graph into descending and ascending form, decreasing and increasing form. Similarly here, and similarly here, that is increasing and suddenly it decreases here. Let us take an example in order to understand the idea of critical point. Here is an example that find the critical point or points of the following functions. There are three functions: f of x equal to x square and f of x equal to x power 2 by 3. We see here that that function is a polynomial, and we see here that the power of x is less than 1, and the function f of x here is a rational function. So for all these three functions we need to find the critical points. First of all, we have taken this function f of x equal to x square. For critical points we need to find the derivative of the function. So find the derivative of this function, differentiate with respect to x this function both sides. The derivative of x square is 2x, so it means that f prime x is 2x. Now for critical values we put f prime x is equal to 0. We see here that f prime x is 2x. This is not a rational function, and nor the power of x is less than 0. So we just need to put f prime x is equal to 0. So it means that we need to put 2x equal to 0, dividing both sides by 2 to get x equal to 0. So x equal to 0 is the critical value of this function x square. It means that at x equal to 0, if you draw tangent upon this function where x equal to 0, so that tangent will be parallel to the x-axis. Similarly, part B, f of x equal to x power 2 by 3. Now differentiate this function with respect to x. That is, we need to use power rule here. So dropping down this power, using power rule to find the derivative of this function, 2 by 3 x power 2 by 3 minus 1. Now taking the LCM of 2 by 3 minus 1, you will get minus 1 by 3. The power of x is negative, so shift it towards denominator to make it positive. So f prime x is 2 divided by 3x power 1 by 3. We see here that f prime is a rational function, that is, there is variable in denominator. So we'll put there is no variable in numerator, so we just need to use the idea for critical values to put f prime x equal to infinity. If there are variable in numerator, we will be using there f prime x equal to 0 and f prime x equal to infinity both. But whenever if there is variable in the denominator, just use this idea that f prime x equal to infinity in order to find the critical values. So f prime x equal to infinity means this fraction equal to infinity, and infinity can be written as 1 by 0. 1 by 0. Now taking the reciprocal of both sides, the reciprocal of this side is 3x 1 by 3 divided by 2, and the reciprocal of 1 by 0 is 0 by 1. 0 by 1 is 0 actually. Now multiplying this to both sides, so that side will become 0 and 2 will be cancelled out from that side. So it will be only 3x power 1 by 3 on the left hand side, and on the right hand side this is 0. Now dividing this equation by 3 and taking cube on both sides to get x equal to 0. So x equal to 0 is the critical value of this function. Therefore, the critical value of this function is x equal to 0. Now lastly, C part, f of x equal to 1 by x. 1 by x can be written as x power minus 1. Differentiate this function with respect to x using the power rule idea, minus 1 x power minus 1 minus 1. So that is minus x power minus 2, and that can be written as minus 1 by x square. So the derivative of the given function is minus 1 by x square. We see here that f prime is a rational function in which x, variable x, is in the denominator. So this is just like part number B, variable is in the denominator. So use this idea. So put f prime x equal to infinity. So it means that minus 1 by x square equal to infinity, and infinity is actually 1 by 0. Now at the same way, take the reciprocal of both sides. The reciprocal of this function is x square by 1, I mean x square, and the reciprocal of 1 by 0 is 0 by 1, which is 0. Now multiplying both sides by minus sign and taking the square root to get x equal to 0. So x equal to 0 is the critical value of this function, f of x equal to 1 by x. So that is the criteria to find the critical values of a function. Now in this slide, the idea for increasing and decreasing functions will be given to you people. That is one definition which is given in your book. Let's say f be a function, f, or you may say that f of x be a function defined on interval I. Interval will be given to you people, and let's say x1 and x2 be any 2 points and this interval I. So whenever, if this x1 is less than x2 and you find the value of f of x1 and f of x2, and the value of f of x1 is less than f of x2 as well, it means that x1 is less than x2. So similarly, f of x1 must be less than f of x2. Then we say that f is increasing function in that interval, on that interval I. That is, this inequality does not change. If you see here, if x1 is less than x2, the same inequality, x1 is less than x2, and whenever you find f of x1 and that f of x1 is greater than f of x2, what does it mean? If this inequality reversed, x1 is less than x2, and we see here f of x1 is greater than f of x2, so this inequality reversed. So in this case, we'll say that f is decreasing in on that interval. So whenever this inequality does not change, we say that the function is increasing, and whenever this inequality changes, then we say that the function is decreasing. A function that is increasing or decreasing on a certain interval, we say that that function is a monotonic function on that interval. Whether that is increasing or decreasing, in both the cases we say that the function is monotonic on that interval. We can define increasing, decreasing functions and another fashion. Suppose that f is continuous on an interval a comma b, and differentiable on a comma b. What does it mean? That if you draw the graph of this function by taking these values of x, the values between a and b, including a and b, and there is no discontinuity of this function, there is no hole in the graph of the function for these values of x, then we say that the function is continuous and differentiable on ab. It means that if you find the derivative of the function, so that derivative of the function exists for any value between a and b. So in that case we say that the function is differentiable on this interval. So suppose that a function will be given to you. If the derivative of the function is positive, greater than 0, if you take the derivative of the function and that derivative is positive at each point of this interval ab, if you take any value between a and b, and for all those values the derivative of the function is positive, then we say that the function is increasing in this interval ab. And whenever the function derivative is negative, less than 0 means negative. If the derivative of the function is less than 0 for all values of x between a and b, then we say that the function is decreasing on this interval. We'll be using this definition throughout to check whether the function is increasing or decreasing. So we may say that these two definitions will be for the purpose of MCQs, and these two definitions will be used throughout to check whether the function is increasing or decreasing. So in order to check whether the function is increasing or decreasing, we need to find the derivative of that function, and we will check that whether the derivative is positive or whether the derivative is negative. Just look at this graph. We see here, we have just studied in the second slide that this kind of line which makes an angle less than 90 degrees with the x-axis, the slope of that function will be greater than 0. The slope of that line, that tangent line or any line which makes an angle less than 90 degrees, acute angle, then we say that the slope of this line is positive. Slope of this line is positive means the derivative of the function is positive. So this whole portion, if you take any point here, and you draw a tangent line on that point, then we see that all those tangent lines are making acute angle less than 90 degrees with the x-axis. So the derivative of the function will be greater than 0, and we see this graph, that this graph goes up from here up to there. It is increasing from here up to there. The height increases. So this function is increasing from a to b, from x equal to a up to x equal to b. This function is increasing. So if the derivative, the slope of tangent line is positive, the slope of tangent line is positive. Positive means greater than 0. Slope is actually the derivative. So if the derivative is positive, then we say that the function is increasing. And from x equal to b up to x equal to c, we see here that this function is decreasing from here up to there. So we say that this function is decreasing, and if you draw any tangent line here or there, those all tangent lines makes an angle greater than 90 degrees with the x-axis. So the slope of these tangent lines will be negative. Slope of tangent line will be negative means the derivative of the function will be negative, less than 0. And whenever the function derivative is less than 0, then we say that the function is decreasing, so it decreases. So that is the graphical idea to understand the meaning of increasing and decreasing. Similarly here, this example will show you people that how could we find the critical values of a function, and how could we know that the function is increasing or decreasing. So both the ideas will be absolutely clear here in this example, that how could we find the critical values, as well as how could we know that the function is increasing or decreasing. I have taken two examples, example A and example B. First of all, we have taken example A, x cube minus 12x minus 5. This is the graph of that function which is given on your book. You don't need to draw the graph, you just need to understand the idea. So that is the function. We need to find the critical values of this function. How could we find the critical values? We have just studied that we need to find the derivative of this function. So find the derivative of this function, differentiate this function with respect to x. So derivative of f of x is f prime x, and derivative of x cube is 3x square. The derivative of 12x is 12 into 1, and obviously derivative of 5 is 0. So f prime x is 3x square minus 12. Taking 3 common from these two terms, we will be left x square minus 4, and factorizing x square minus 4 in this fashion. So that is the derivative of the given function. We see here that the derivative of the function is a function which is not rational function. So we will be using here to find the critical values that idea, that put f prime x equal to 0. So putting f prime x equal to 0 means put this equal to 0, dividing by 3 to get this equal to 0. It means that either x plus 2 is 0 or x minus 2 is 0, shifting plus 2 towards right hand side and minus 2 towards right hand side to get x equal to minus 2 and 2. So these two are the critical values of this function, and this is clear from this graph. This is the graph of this function. If you look at this minus 2, whenever x equal to minus 2, we will be getting this point, and whenever you draw a tangent line at this point, that tangent line is parallel to the x-axis. So this is the critical point. And if you look at here, this is x equal to 2. For x equal to 2, we have obtained this point, and whenever you draw a tangent line, that tangent line will be parallel to the x-axis. So these two are the critical points, and the derivative of the function on these 2 points will be equal to 0. That's the idea. Anyways, we see here that these 2 critical points divides this whole graph. We may say that these 2 critical points, minus 2 and plus 2, divides this whole real line in this fashion. These critical values, minus 2 and 2, there is minus 2, and on the left hand side there is negative minus infinity, minus 2, minus 1, 0, plus 1, plus 2, and so on, so on, so that is plus infinity. So these 2 critical points divides the whole real line in this fashion. We can denote this interval in this form, open interval. This is an open interval. This interval do not contain minus infinity and minus 2, but all those numbers which lie between minus infinity and minus 2 are including here. We may say that minus 3 is here, minus 4 is here, minus 5 is here, minus 10, minus 100, all values are there. And just look at this interval. This interval is again an open interval, and in this open interval minus 2 and 2 are not included. All those values between minus 2 and 2 are included here, namely 0, 1, 1.1, 1.2 and so on. So all those values are included here. Similarly, 2 up to infinity is denoted by this interval. So 2 comma infinity is an open interval containing all those points between 2 and plus infinity. So these two critical points divide the whole real line in this fashion. First of all, we'll take f prime x, which is equal to 3x square minus 12. 3x square minus 12. Take the derivative of the function. Now these are the critical values. That is the answer for the first portion. Find the critical values. That is the answer for that. And now we are in search of whether the function is increasing or decreasing. So we have these three portions in front of you. These three portions. Take f prime x and take any value between minus infinity and minus 2. So I have taken minus 3, which belongs to this interval. You can take minus 4, minus 5, minus 6, minus 100 as well, but take only a simple and short value in order to calculate f prime x easily. So I have taken minus 3 between minus infinity and minus 2 here. So put minus 3 in this equation 1. Whenever you put x equal to minus 3 here, so that will become f prime minus 3. That will become 3 into minus 3 whole square minus 12. Minus 3 whole square is plus 9. Plus 9 into 3 is 27. 27 minus 12 is 15. So this is 15, not 27. Correct this number, that is 27. That is 15, not 27. But we see that this 27 is positive. This 27 is positive, and whenever the derivative of the function is positive, then we say that the given function is increasing. So for this interval we have taken only one value, minus 3, and for that value the derivative of the function is positive number. So we say that f of x is increasing in this whole interval. Now take any value between minus 2 and plus 2. You can take 0, 1, 1.1, 1.2, minus 0.1, minus 1.1, whatever you want to take the any value in this interval. The simplest value in this interval is 0. So I have taken 0, which belongs to this interval, and put 0 in the given equation. Put x equal to 0 and the derivative of the function. So whenever I put here x equal to 0, I obtained f prime 0. This is actually f prime. So that is f prime 0 is equal to 3 into 0 square. Square is missing here. Minus 12. 3 into 0 is 0. So we are only left with minus 12, and we see that minus 12 is negative, less than 0. And whenever the derivative of the function is negative, we say that the function is decreasing over there. So we will say that f of x is decreasing in this interval. And lastly, take any value between 2 and infinity, any value, 3, 4, 5, 6, 7, 110 and so on, so any value. So I have taken 3, which belongs to this interval, and put x equal to 3 in equation 1, this equation 1. So put x equal to 3 here uh, we get 27 minus 12 equal to 15. So again 15 is missing here, so that is 15, and 15 is positive. So 15, the derivative of the function, that is actually f prime 3. F prime is missing here. I'm going to correct this f prime. Now here we are, we have taken the derivative of the function 3x square minus 12 here, taking this first interval, any value between minus infinity and minus 2, which is just been discussed. I have taken x equal to minus 3 belongs to this interval, and put this x in equation number 1 here. Whenever you put x equal to minus 3 here, we'll be getting f prime minus 3 into minus 3 whole square minus 12, and 15 is the answer. Now we see that 15 is greater than 0. Greater than 0 means positive, so f prime is positive. So it means that the given function is increasing in this interval. Similarly, take x equal to 0. We have taken this interval, 0 is including here. You can take 1 as well, but 0 is the simple one. Take x equal to 0, which belongs to this second interval, and put this x equal to 0 in equation number 1 in the derivative of the function. Whenever you put x equal to 0, we have obtained f prime 0 minus 12. Now minus 12 is less than 0, negative. So f prime is negative, it means that the function is decreasing. So the function f of x, the given function f of x, is decreasing in this whole interval. Similarly, the last interval is left, 2 comma infinity. Take any value between 2 and infinity. You can take 1, you can take 3, 1 is there, okay. You can take 3, 4, 5, 6, 7, and so on, so take the simple value 3 between these two values. So put x equal to 3, which belongs to this interval, and this equation 1 in the derivative. Whenever you put x equal to 3 and that equation, we obtained 15, and 15 is greater than 0. Greater than 0 means positive, so it means that the derivative of the function is positive within this interval, so the function itself is increasing in this interval. So that is the idea for increasing and decreasing functions. If you look at the graph of this function, the graph of this function is here. See here, that is the critical point, the critical value minus 2. Up to minus 2, we see here, if we increase the value of x from left to right up to minus 2, the graph goes upwards, increasing. So minus infinity and minus 2, for between minus infinity and minus 2, the graph is increasing. So between minus infinity and minus 2, the graph of f of x is increasing, the function is increasing. Similarly here, between minus 2 and plus 2, that is the graph of the function, between minus 2 and plus 2. If you increase the value of x, the graph of this function goes down and down and down. So we may say that between minus 2 and plus 2, the graph of the function is decreasing. So that the function is decreasing between x equal to minus 2 and x equal to plus 2. That is this idea, that between minus 2 and plus 2, the function f of x is decreasing. And if you look at this portion, from 2 up to infinity onward, from 2 up to onwards, if you see that from 2, the graph is increasing, it goes up and up, increasing. So we may say that the function is increasing from x equal to 2 up to infinity. So that is this thing, that the function is increasing from 2 up to infinity. Similarly, take this b part, that is part b, and this slide we have taken this function and differentiate this function with respect to x. Whenever you differentiate this function with respect to x, use the power rule in this fashion. Similarly, the power rule in this fashion. Simplify this power and this power as well. You'll get 1 by 3 here and minus 2 by 3 there. This minus 2 by 3 is negative, so shift it towards denominator, and 4 by 3 is common in these two. So taking 4 by 3 common, we will be left with x power 1 by 3 minus x power minus 2 by 3. Shifting this x towards the denominator and take the LCM of these two terms. X power 2 by 3 is the LCM, 3 is here with x power 2 by 3, and whenever you multiply x power 2 by 3 with x power 1 by 3, the powers will be added, and by taking LCM you'll be getting x power 1. 1 by 3 plus 2 by 3 is x power 1 multiplied by 4 minus 1. So that is actually f prime x. For critical values, we see that in this f prime is actually a rational function which contains variable and numerator and n denominator. Both portions contain the variable x, so we will be using both the conditions for the critical values. So for critical values, we'll put f prime x equal to 0 and f prime x equal to infinity as well. Remember that. So whenever f prime x is equal to 0, it means that this rational function will be equal to 0. Multiplying both sides by 3 into x power 2 by 3, that will be cancelled over here and that will become 0. So 4 into x minus 1 is equal to 0. Dividing by 4 to get this equation and shifting 1 towards that side to get x equal to 1. So x equal to 1 is one critical value for this function. Now similarly, f prime x is this function, the same f prime x, but on right hand side there is infinity, and infinity can be written as 1 by 0. Now taking the reciprocal on both sides, the reciprocal of this rational function is this thing, and the reciprocal of 1 by 0 is 0 by 1. 0 by 1 is actually 0. Now multiplying 4 into x minus 1 towards that side to get 3 into x power 2 by 3 equal to 0, and dividing this equation by 3 to get x power 2 by 3 is equal to 0, and taking 3 by 2 power on both sides to get x equal to 0. So that is the second critical value for this function. So we have two critical values, x equal to 1 and x equal to 0 for that function. So that is the answer for the first part, that the critical values are 0 and 1. Now these critical values divides the real line as minus infinity up to infinity, include 0 between minus infinity and plus infinity, and include 1. So this whole real line is divided into 3 portions. This portion can be written as minus infinity comma 0, this portion can be written as 0 comma 1, and this portion is 1 comma infinity. So this open interval contains all those points between minus infinity and 0, and this open interval contains all the points between 0 and 1, and similarly here between 1 and infinity. So we are left with these three intervals. We'll be taking three values, one value between these two, one value between 0 and 1, and one value between 1 and infinity to check f prime x. That is f prime x. That is equation 1. Now take one value, say -1 here. You can take -2 as well, -3, -4, but -1 is simple enough. So -1 belongs to -infinity comma 0. So put x equal to -1 in this equation. Whenever you put x equal to -1 here, we'll be getting x prime -1 equal to 4 into -1 divided by 3 into -1 power 2 by 3. -1 is -2. -2 into 4 is -8. And -1 square is there. So -1 square is +1. +1 into 3 is 3. So we see here that f prime -1 is -8 by 3. That is a negative number, means less than 0. So f prime is negative, or f prime is less than 0. So it means that the given function is decreasing in the given portion. So the given function is decreasing in this interval. For all those values of x, the graph of function will go down and down. Now take this portion, take any value between 0 and 1. Say I have taken 0.5, which belongs to 0 and 1, and put this 0.5 in the derivative of the function. Whenever you put x equals 0.5 here, you'll be getting this answer, and this answer is actually negative. So f prime is negative, so again the function is decreasing, and the function is decreasing in this portion. So for both these two portions, the graph of function will go down and down. Now the last interval is left. Taking the last interval, one value here, say 2, you may take 3, 4, 5. Take x equal to 2, which belongs to 1 infinity, and put this 2 in equation number 1 in derivative of the function. Whenever you put x equal to 2 here, we'll be getting this answer, and see this answer is positive. Positive means greater than 0. So the derivative of the function is greater than 0. Whenever derivative of the function is greater than 0, we may say that the function is increasing in the given portion. So the function f of x is increasing in this given portion 1 comma infinity. So that is the answer for the question. If you look at the graph of that function, you do not need to plot this graph. You just need to look at the situation over here. The graph of the given function is just like that. We see here when x it goes just like that. It goes up and up just like that. So minus infinity, if you go from minus infinity towards 0, so minus infinity towards 0, we see that this graph goes down and down and down and down. So between minus infinity and 0, the graph of the function is decreasing. And if you look at this portion 0 comma 1, 0 comma 1, between 0 and 1, the graph of the function goes down and down again. So we may say that between 0 and 1, the function is decreasing. It goes down and down. Now suddenly when you reach 1, and after that suddenly the pattern of the graph changes and it goes up and up, just like that. So we may say that from x equal to 1 up to infinity, the function goes up and up. It means that the function is increasing from x equal to 1 up to infinity. That is the graph of the function. So this is the end of this lecture. In this lecture we have studied about the critical points, the critical values of a function, and the idea for increasing and decreasing function. a short assignment will be uploaded after the lecture. You need to solve all those questions in order to realize the idea of those two topics.